In this video, we'll cover acid and base titration. I'd like for you to take a look at this particular scenario. Say you were in a very big collision and the opposite driver has a potential to have DUI. The problem is this opposite person who hit you, well, he passed away. Now, the thing is, you can't take a breathalyzer with a person who's dead. So a police comes around, and what he does is he collects a sample of blood. Then what happens is he takes that blood sample and takes it to the lab, a forensic lab. The forensic guy, what he's going to do is he's going to test out whether this blood sample has alcohol or not through a process called titration. In this titration process, in the flask, there will be a blood sample. And over here, there's going to be a dichromate sample. And the dichromate and the blood sample in here, they're going to interact together. And depending on how much dichromate is needed, right, how much has been dispensed to see how much alcohol you have, well, that kind of determines the blood level alcohol. And the blood level alcohol, say this person that happened to hit you and quite hard, had a 0.09 BAC, blood alcohol level. Well, that means it's a 0.09 grams of ethanol is present for every of its 100 ml of his blood. So what does that mean? Was this person, did he have a little too much to drink? Well, maybe you could find out. The blood level, alcohol level is something that you can find out on your own. But my point is mainly in this part. The titration is very important and applicable in the real world. Now, this was a blood alcohol, and also it was titrated with a solution called potassium dichromate. But on your end, in our experiment, in our class, we're going to deal with an acid and base titration. In an acid-base titration, it's an experiment to acquire information about a solution containing an acid or a base. What is that information? You're trying to look for the concentration of an acid or a base. Here, I'll illustrate a little further. So if you have a sample in here of an acid, so say this is acid, but you do not know its concentration. Do not know the concentration. Then you add in a base here, but you do know the concentration with known concentration. Now, this particular base is going to be titrated by administering the drop-by-drop format into this flask, into the acid. At a certain point in time, this solution is going to turn light pink, a little bit darker pink. And what you're going to do, you're going to stop at that point. And depending on how much you have displaced in that base, you can tell what the concentration of acid here is by calculation. So our goal today is to calculate how much concentration would this be, and maybe even the pH. What is the pH level here? We can generate what is called a titration curve as we look at this titration. In this titration curve, there are two components in the x and the y axes. On the y-axis first is the pH. Then the x-axis is the volume of the titrant added. So what is that titrant? I'm talking about the NaOH added. So here's my base, NaOH, for example. And say example for this acid is hydrochloric acid. So some kind of acid and some kind of base, but we know the concentration of this, but we do not know, unknown, concentration of the HCl. So let's look at the very beginning before any titrant or any of the base has been added. The pH is very, very low because you just have acid. Then as more and more base is added, you can see that the pH level starts to rise because there is base present. Now, at a certain point, what is called the equivalence point, this is a point in which the concentration of the acid and base are exactly the same. And so at this point, it's called the equivalence point, and that is a point in which the solution will most likely turn slight pink if you had added what is called an indicator. If you didn't, it'll just remain clear as pretty much forever. And you add more and more base, and so the pH level significantly rises, and then it levels off based on what the concentration of the base was from the begin with. So again, in the very beginning, there's only acid present, so the pH is really low. In the very end, you see the pH is very high because you added a lot of base. Somewhere in between right here where there's a big jump, that is a location where the acid and base concentration is exactly the same. Now, I want to go a little more deeper into this concentration, and I want to target the strong base, strong acid titration. So what do I mean by strong acid? In this flask is going to remain a strong acid. And what you're titrating in, the addition is the strong base. So something like this, NaOH and then HCl coming in through. So if I have NaOH, which is the strong base, and you can also tell by NaOH being the strong base by looking at your reference sheet. The chart says that sodium hydroxide is a strong base. And strong acid, HCl, well, how did I know that was a strong acid? That was in one of the charts of the reference sheet as well. Now, this strong acid and base are coming in. So strong base is coming in as seen in this slide. Once the base hits right here, and it reacts with the hydrochloric acid as shown above. Now you'll notice that the strong base will take away the hydrogen, and the hydrogen will donate its hydrochloric acid from the hydrochloric acid. So therefore, H and the OH form water. And then the rest, the sodium and the chlorine, combine together to form sodium chloride. Here, I want you to identify the spectator ions. If you don't know what a spectator ion is and you need a little refresher, you might want to check out the video that says Strong Acid and Base Review. The spectator ions, I want you to take out all of the spectator ions as shown here. Spectator ions are sodium. Spectator ion here for hydrochloric acid is chlorine. Therefore, the sodium here is gone and chlorine is gone. So what you're left with is just the strong base plus the hydrogen ion, and then you have H2O. Now you see that there's a double arrow, but that shouldn't be it. It should be a full arrow. And that's because in a strong base and acid reaction, it's always going to go in one direction, and it's very, very little is going to go to the reverse reaction. So it's not going to reach any equilibrium. It's just going to go driving forward. So at this point where it's neutralized, meaning that the concentration of the acid and base are exactly the same, there's just pretty much just water or salt water, but we're not indicating the NaCl in here, so we're just going to put it as water. Let's take a more closer look at the graph here. So in the very beginning, you just have acid. That's referring to this point. As base is being added, you see the pH starting to rise. Then after a certain point in time, you have an equal amount of hydroxide and equal amount of H plus, then that is which you're at equivalence point. And in this case scenario, the pH is 7. So we can say that when a strong acid is reactive with the strong base, so always the strong acid, and if it's a strong base, the equivalence point is going to be always at 7, at pH of 7. This is because it's the conjugate acid, the Na and the Cl, and the conjugate base are neutral, so they don't participate in the reaction. So therefore, they don't contribute to the pH level changes. So let's do a little bit of our example regarding the strong acid and strong base titration. Here it says, what is the pH when 50.0 ml of 0.100 molarity of hydrochloric acid is added to 49.00 ml of 0.100 molarity of NaOH solution? So here what it's saying is, hey, you have acid of 50 ml here. And the concentration of this particular acid is 0.100 molarity. And then you add 49.00 ml of 0.1 molarity of NaOH. So here you're going to add 49. From there, you're going to pour down 49 ml of 0.100 molarity of NaOH. So after you have titrated, and we don't know if it's at this point, but whatever it might be, what is the pH after those amount has been titrated? Okay. So the very first thing you want to do is that you want to recognize that this is not an equilibrium. So this is wrong. This should be a straight arrow, that this is a straight arrow point. It's not at equilibrium. So what we can utilize is the ICF table. We're used to ICE table, where we talk about equilibrium. ICF refers to that it's going to into the final point. It's not going to reach any equilibrium. So we're going to use that table. Let me go ahead and rewrite this equation. So I have my OH minus. I'm not including any of the spectators. So let me take out all of the spectators to avoid confusion. Plus H plus, and then that goes to water. Now hydroxide here, it has hydroxide, H, and H2. So I'm going to put ICF. Okay. Then all of these guys are going to be in millimoles. Rather than molarity, we're going to put it in millimoles. So how do I find the millimoles of hydroxide? So let's talk about hydroxide first. So 45, you're going to multiply the 45.00 ml of 0.100 moles over milliliter. Oh, over liter, I'm sorry. Molarity is moles over liter. You're going to multiply this by the milliliters with the moles over liter. And this is for our hydroxide here. And if you were to multiply this out, you can cancel out just the liters, right? And 49 times 0.1 would be, if you punch this into the calculator, then you would get 4.9 millimoles of sodium hydroxide. Okay, so here I'm going to write 4.9. What about for the acid, or H plus? H plus, that's referring to this one. It's got 50 ml multiplied by the concentration, which is 0.100 moles over liter. cancel out the liter, and you would get 5.0. Oh, I should keep the sig base 4.900, 4.90, and then 5.00 millimoles of HCl. So that's just saying it's of the hydrogen. Okay. And then this is water is liquid, so we don't need to account for these guys. Okay. What about the change? Now, because this is going to be used up all the way till the end, one of these guys are going to end up becoming 0. So which one is the smallest millimoles? Right, the hydroxide is the smallest millimoles. And 4.90, you're going to subtract that particular one because this is our limiting reagent. And so we subtract 4.90, negative 0.90. In the final, at the very end, you would be left with, if you add the top and the bottoms, you add the I and the C, then this becomes 0. What about for the hydrogen? 5 plus the negative 4.90, this would end up being 0.10. Okay, 0.10 millimoles of hydrogen ion. Okay. Now, this is not a concentration, so convert this into concentration. What is concentration? Concentration unit is moles over liter. So we know that concentration of hydrogen, therefore, we have the moles, well, we have millimoles, and then we're going to divide it by the total volume there we have collected. And we collected 50 plus the 49. 50 plus the 49, 50.00, 50.0, I apologize, plus the 49.00. So that should equal to 99.0 milliliter. So if I want, this is my total volume. And if I want the concentration of H plus, I want to take the millimoles over the total volume in milliliters, which is 99.0 ml, and cancel out the m's. Okay, that gives you moles over liter. That's going to give you the concentration. So if you punch this into the calculator, you would get 0.0010 molarity, okay, approximately. So that was my concentration for H plus after this reaction has gone into place. Now, what it's asking for is not the concentration of HCl in the end, but rather the pH. So we know that pH is equal to the negative log of hydronium concentration. Hydronium concentration is the same thing as concentration of H plus, and we have that, which is right here. So we're going to plug that in, negative log of 0.0010. Okay, so go ahead and punch that into the calculator and then come back to check the key. You'll notice that this would become approximately 3.0. So that's how much acidic this point is. So if at pH of 3, we were right here at this point, around this point right here. So hopefully that sort of makes sense. And then we'll do some more problems for the next few videos.